I will ask you to suffer through one more boring and technical lecture, and then it gets more interesting from the next one, because we will be doing something that's directly related to chemistry. But today we need to prepare ourselves. So the next lecture will be multivariate optimization. This is how you make lots of money and reduce your costs in chemical engineering, for example. But today we will be gearing up. And it's an extension of derivatives that we will be looking at today. You, of course, realize by now that very few variables in chemistry and physics actually depend on just one thing. Normally, your energy or your cost or your yield will depend on multiple parameters: pressure, volume, temperature, spatial location, and other things. And so we need today to put some formal grounding for differentiation of multivariate functions. Now, partial derivatives themselves are almost trivial. You just assume that all other variables are constants when you differentiate. But the difficult thing is that there are three different chain rules when you do partial derivatives, and this is something that we need to cover today. So the first item on the agenda is partial derivatives. Partial derivatives. At the utilitarian level, what we mean by a partial derivative is that every other variable is assumed to be a constant. If you take, for example, d by dx, and notice the curly d's that designate partial derivatives of x, y, z, even though this depends on three variables, it's a product, we only have to differentiate this with respect to x and assume that y and z are constants. And so this is just y, z. And then if we have another example of something slightly more complicated, d by dx of 1 minus x over sine y, then again, if y is a constant in this context, and we are differentiating with respect to x, then we can simply take this out of the bracket. So this will be 1 over sine y d by dx 1 minus x, and the derivative of that is of course minus 1, so that is minus 1. So simple recipe when you are seeing partial derivatives is that every other variable is to be assumed constantly. Formally speaking, we can also give the partial derivatives a limit definition, so it will be df by dx of some multivariate function. Let's say we have by dx of f x, y, z, perhaps something else, maybe time. Then that's a limit of delta x equal to 0 of the function where only x has been incremented, so f x, y, z, and whatever else remain unchanged, minus the original function, f x, y, z, whatever else, divided by delta x. So we simply more or less ignore the presence of other variables and differentiate with respect to the variable interest. Now, as I mentioned, this is trivial, you will very quickly learn it, but the difficult thing is the chain rules. So, and that is what most of today is going to be about. Chain rules. You have seen this already in the previous lecture when we dealt with the finite increments, remember the correction functions and so on. You've seen the following type of relation. The delta f, the change in the function, is df by dx x plus what we had as a correction function. I will not prove this statement, it will take a very long time, but I will simply ask you to take my word for it that the correction here is of the order of delta x squared, and this notation, big O, means that whatever this is, this asymptotically, as delta x becomes very big or very large, behaves as delta x squared. We don't need to know what it is, we don't need to know what's inside in there, it's just some quantities that drops off as delta x squared when delta x becomes smaller and smaller. And you can perhaps remember the geometric definition of the derivative from your school times. If we have some function x, this is x, and that is f, then the derivative was the slope of the tangent line that is touching your function at some particular point. And indeed, if you look at this with respect to delta x, this is a linear function in the leading term, and that is the slope of the corresponding tangent line. So we will be using this a few times with respect to various variables that f may depend on. But I have not given you a full proof for this because we really have quite limited time in this course. Okay, so let us proceed and try to consider a situation where we have multivariate functions that are nested. In particular, we will look at something like this. d by dx, f that depends on g, that itself depends on x, y, z, and perhaps something else, but I will just skip the dot. So we are doing a partial derivative of a nested function where it is the bottom layer that actually depends on x. Well, we do it the usual way by considering increments and then considering the limits of those increments. So I will rewrite that as slightly perhaps more compact. So slightly more compact formula. Limit delta x going to 0 of delta f over delta f is this increment of f that we have in the numerator, and delta x is the increment of x that we have there in the denominator. Okay, so our delta f, as per the formula here, this was f of x. This is now f of g, because it immediately depends on g, and then g depends on something else. So we will have dg times delta g times something of the order of delta g squared. But delta g itself is also a function, and we can apply the same formula now to g. We can say that delta g itself is also dg by dx. Notice the partial derivative because it depends on multiple things. Delta x plus something of the order of delta x squared. And there are no further variables in here because we assume that they are constants. There are no increments of y and no increments of z. What we do is we take this and put it here to replace that delta g. So we can continue this formula here. It is df by dg times dg by dx delta x plus the term of the order of delta x squared plus the term of the order of delta g squared. So far so complicated, but let us now, because we now actually have the delta x, divide by it to bring this into a form that directly corresponds to a derivative. So we will have delta f by delta x. So I have divided both sides by delta x. Is df by dg, dg by dx. Notice that the derivative with respect to g is full because f only depends on g. But the derivative with respect to x here is partial because g depends on other things as well as x. So delta x divided away plus something of the order of delta x. So here notice we divide delta x squared by delta x, so this becomes order of delta x. This is assumed to be a finite number anyway, so if something was order of delta x times a finite number, it's still order of delta x, so this O absorbs all constant factors, plus something of the order of delta g squared divided by delta x. And let's now take a look at what happens when we take the limit of delta x going to 0. Take that and use the limit. Well, delta f by delta x clearly becomes just the derivative. So this is d x. That stays put. F by g times dg x. This clearly goes to 0. So something that was of the order of delta x goes to 0 when delta x goes to 0. And let's now take a look at this. In the numerator we have delta g squared, and delta g is at least first order in delta x. So in the numerator we have something of the order of delta x squared, in the denominator just delta x, and so this also goes to 0. And so what we are left with is this expression, and this is the chain rule for the partial derivative of a function in a situation where it's nested like this. This is our situation. When f depends on one function, that is itself a function of many other variables. df by dx partial is df by dg full times dg by dx partial. And we'll have some examples later in this lecture. You will have plenty of examples in your practical classes later. So let us consider the opposite case, when we have a situation where f depends on multiple things, but each of them depend on something single, for example, time. We would have this quite frequently in physics, that the cost or the yield of your reaction depends on multiple parameters, but they're also a function of just time. So we will have something like this: d by dt f of x of t, y of t, z of t, and so on. For example, the energy of some charge as a function of its location on some trajectory. And this is the full derivative because the whole thing ultimately just depends on time. But there are multiple things inside f, and we have them to thread through the derivatives somehow. Okay, so what I'll do is I will do now an extension of this. In the event when we only have one variable, we have just this increment with respect to x. In the event when we have multiple variables, we will have multiple terms here. So df by dy, df by dz. The first thing we need to do is to say delta f will be df by dx delta x plus df by dy delta y plus so on, plus lots of residuals. Order of delta x squared, order of delta y squared, and so on. But x and y themselves also depend on time. So then delta x is dx by dt delta t plus order delta t squared. And likewise for the y variable. So we take this and we substitute it here, and we also substitute its brother for y into y, and we continue this expression. So we have df by dx, and then that thing inside, dx by dt delta t plus order of delta t squared plus df by dy and dy by dt delta t squared, and all the various corrections in there. What we can now do is, just like we did in the previous round, we can divide both sides by delta t and see what is going to happen. So, delta f by delta t is df by dx dx by dt plus df by dy by t plus all sorts of correction terms that we have there. Z will vanish in the same way as they did here when we take the limit, and therefore in the end df by dt becomes df by dx dx followed by dt plus df by dy followed by dt, and so on for any other variables that f might contain that also depend on time. This is our second chain rule. So that was number 1. This one is number 2. This was for the case, the first one was for the case when f depends on one thing that then depends on many. This is for the opposite case when f depends on many things that say f depends on one. And of course there's the third case where f depends on many things that depend on many things in their turn. But I would skip that derivation. For some reason it's just horrendous, right? So this we could fit into the board. This we could sort of also walk through. But if you do the full many chain rule, it's like a couple of boards of writing, and so I will simply just give you that formula. And although it looks large, it actually eventually surprisingly intuitive. So if you have f that depends, let me see the notation on, so let's say d by d alpha, some variable, for f that depends on x, that depends on alpha, beta, gamma, and so on, that y depends on alpha, and so on, and so on. So this f that depends on x, y, z, and such, where each of them also depends on the Greek variables. So that is equal to df by dx dx by d alpha plus d y dy alpha and so on. The reason why this is easy to remember is that it is sufficient to just remember the usual chain rule. The rest of it is just extensions. You simply have the derivative of the outside function. If the outside function depends on only one thing, the derivative is full. If it depends on many things, the derivative is partial. And then you take that derivative with respect to the argument, and then times the derivative of the argument. That's the usual chain rule, right? And then if the argument depends on just one thing, then the derivative is full. And if the argument depends on many things, then the derivative is partial. And it's just a combination of the two rules in the case where we have everything depending on everything. Okay, I think what this calls for is write a few examples. This is probably the most obscure piece of writing in this entire semester. So bear with me. So, examples. Let's say we have Z that is a sine of x. However, x is u squared b squared. And we would like to have dz by du. Well, clearly here we have the first case. Z only depends on x, and then x depends on u and on v. So this is dz by dx dx by du. The rest you know. It's trivially easy to differentiate a sign with respect to x, which is the cosine x. And then trivially easy to differentiate x with respect to u. Remember that d is a constant in this case, the derivative of u squared is just 2u. So 2 squared, and that's the answer. So for all the horror that we were writing there, this is the rigorous derivations of the corresponding rules. Their application is actually quite trivial. The second case, when we have z, that is x squared y minus y squared, where x is t squared and y is just 2t. This is the second case, where z depends on multiple variables, but those variables individually are just a trajectory of some particles that flies in a two-dimensional space. And we would want dz by dt. Full derivative, because everything ultimately only depends on time. So, we have two variables in here, so this will be dz by dx times dx by dt plus dz by dy by dt. So chain rule with respect to every variable that occurs in z. Individual derivatives are again trivial. Dz by dx is 2xy. Then dx by dt is 2t plus dz by dy minus 2y times dy by dt 2. Notice here that we have a mixture of xy and time. I would not insist on this because the differentiation is complete, but cosmetically for visual reasons, I suppose, reasons of elegance, it's useful to just translate everything into time. And so we have 2t squared, which is x, then times 2t, then times another 2t, and then minus 2y, that's 4t times 2, 8t. And so in the end, we have 8t to the 4 minus 8t, and that's as much as we can simplify that. I think I've missed something because in my handout it's a 10 in there, but I will leave it as a homework to find out where I made the mistake. There is mistake. Okay, so that's the second case. The third case, let us look at something rather horrendous on the surface. So that will be the exponential of x squared y, where x is root uv and y is 1 over d. So technically speaking, we have z that depends on two variables, and each variable depends on two more, although u doesn't appear, which is primarily just 0 times u. Technically speaking, it depends on, but in practice the derivative is going to be 0. Okay, and we want dz by du. dz by du, well, the usual. dz x dx by du plus dz by dy du. Individual derivatives are not necessarily easy in this case, right? So dz by dx in here will be a chain rule in its own right. You have the exponential and then you have the square. So the derivative of the outside function there is the exponential e squared y times the derivative of the inside function with respect to x, 2xy. So that is this. dx by du, So again, we have a root. So this is going to be 1 over 2 roots u v. And v is basically a constant in here. And I think that's actually not right. It's 1 over 2 root u times root v. Because v doesn't participate in the differentiation. So we can just take it out of the bracket. Okay, dz by dy plus z is that exponential, and so again a chain rule ex squared y times the derivative of the index with respect to y, just x. So this is dz by dy, and then dy by du is just 0. 0, and so that doesn't actually contribute. So what we are left with is this, where it would be useful if we again translate everything into u and v, because we have a mixture of x's, y's, u's, and v's. So if we have the exponential, x squared is just uv, then y is 1 over v, 2xy, 2 root uv, and then y over v, and then 1 over 2 root u, and root v. A lot of things will cancel. Notice that in here we have v over v, so this is e to the u, then there should be a 2 in here. 2 cancels 2, root u cancels root u, root v times root v is v, cancels v, so that's actually the final answer to u in this case. Okay, so to summarize the chain rules, I will remind you the usual chain rule. We have d by dx f of g x. This is df by g times dg by x. So the derivative of the outer function with respect to its argument times the derivative of the argument with respect to whatever it depends on, possibly continued if you have multiple nested functions. Hence the main chain. In the multivariable case, we can have situations where the second function might depend on multiple other things, in which case this opens up. So you will have, where is it, df by dg, dg by dx. You have to specify the partial derivatives with exactly what it is that you are differentiating with respect to. Then the opposite situation is when the function depends on multiple things that in turn depend on just one variable. After a while, we get the second rule, where you have to expand the partial derivatives of everything that f depends on, and then the full derivatives with respect to, for example, time. And then the final case is a partial derivative with respect to the first layer of arguments times partial derivatives with respect to the second layer of arguments. Initially obscure, takes a lot of training and getting used to, but absolutely all equations, Schrödinger's equation, Navier-Stokes equation, Fokker-Planck equation, even Black-Scholes equation used in option pricing in economics, they're all partial differential equations. And they all take the functions that are functions of multiple things, and themselves functions of multiple things. And so, difficult and obscure as this is absolutely essential. And you'll see that in the next lecture as well. Now, in preparation for that thing, we need to introduce a few more objects. One is called the gradient. And the gradient of a function is a vector of all of its derivatives. If we have a function f, y, z, for example, then something called nabla F, the inverted triangle is called nabla, is a vector d by dx, d by dy, d by dz applied to F. Notice that I have written this in the operator form. So this acts as an operator from the left on the F. So this is equal to d by dx, d by dy, and d by dz. Let us take a look at the geometric meaning of this thing. Why would we want to put partial derivatives into a vector? Let's, for example, take something like that. X and y equals x squared plus y squared. With respect to both x and y, this is a parabola, and so in 3 dimensions, this is going to be, of course, called a parabola. Draw ourselves a system of coordinates and take a good look at what that thing is. So, draw a function, be a surface. From the side, and if we sit somewhere here, let us take a look at what that vector would be. So df by dx is the direction of, well, it's the sign of whether the function grows or decays. So this is x, this is y. So the function grows most steeply in the negative direction of y and in the negative direction of z. So if we look at where it grows the most steeply, it's this direction here. And then if we take the projection of this onto the xy plane, there will be the corresponding vector here pointing somewhere away. And so this projection, like that, is called the gradient. So this is number f, whereas that is f of y. Sometimes people draw an arrow on top of that number to emphasize that that's the gradient. And you can see that that is basically the direction of the steepest growth. So the gradient of the function gives you the direction in which that function grows most rapidly. You will see in the next lecture that this is extremely useful, because if we are, for example, looking to maximize the cost of producing a certain chemical, it really helps to know in which direction that cost grows the most steeply, so that we don't want to go in that direction. And conversely, the negative of the gradient will be the direction in the parameter space of whatever physical problem where the cost is reduced the most steeply. And so it would make sense to make an alteration to our experimental parameters in that direction. So this is the gradient vector, and this is why it is useful. The second place where partial derivatives occur is vibrational spectroscopy, so infrared and such, where the energy of a chemical system, so for example, for a single particle, if it's attached to the wall with a spring, the energy is mv squared over 2 for the kinetic part, and then kx minus x naught squared over 2 for the potential part. If you remember the standard spring with a force constant k, and there being a mass here. So you will have some equilibrium lengths for this spring, x naught. And if you try pushing it or compressing it, then the energy rises, and as you know from Hooke's law, it rises quadratically. And then that's just the standard kinetic energy. Imagine now that we have multiple particles that are connected by springs to each other. So the molecular energy in that case will be every possible velocity that our particle has. So it will be 1/2 a sum over all particles, the mass of each particle times the velocity of each particle, absolute square. So the modulus of that vector, because it will be a vector in 3 dimensions, and then square. So that's the kinetic part. And then the potential part, if you have multiple particles all connected by springs, for example 3 in here, somehow I think, each individual spring, each individual chemical bond will have its own force constant, because bonds differ in how strong they are, and we need to sum over all the bonds that there are in the system. So it will be 1/2 a sum over all pairs of particles, but we don't want to count that twice, and so this is sum for n greater than k, and then k and m, the force constant of the bond between particle n and particle m, and then the location of particle m, so the bond length, minus r m equilibrium bond length, and all of that we would want absolute square. So, fairly complicated expression, but what is important here is when you look at the second derivative of this, for example, so d2e by dx squared, differentiate this twice with respect to x, you get k. So the force constant is the derivative, the second derivative of the energy. But the force constant is related then to vibrational frequencies. You may remember that the vibrational frequency is root k over m. And so if we know all second partial derivatives of this, we do know all vibrational frequencies, and then we can match molecular structure to infrared spectrum, for example. And this is extremely useful. And what we therefore need to know in the case of the full molecule are the following things. d2e by dxm dxm, where that is some coordinate of some particle and that's some other coordinate of some other particle. And if we put these objects into a table, the table is called a Hessian. Hessian matrix, after evaluation by the name of Hess, that contains all second partial derivatives of molecular energy with respect to positions of all the particles, and then the structure of that matrix, we will get into that in semester 2, is related to the vibrational frequencies observed in the infrared spectrum, which are then in turn related to molecular structure, and this is how molecular structure determination with infrared spectroscopy actually proceeds. You predict the theoretical frequencies, you see if they match the frequencies that you see. If they do, then it might be your substance. But if they don't, then very definitely isn't your substance. It's an interesting and complicated game, structure determination, but this is where it is useful. So, two principal uses. One is optimization of anything, both maximization and minimization, and the other is quite a lot of things across various chemical spectroscopies. Now, I don't actually remember which way around these things were. We probably wanted that way. So that's the difference of the current length from the equilibrium length for a given bond. Okay, so the summary of today is the difference between the full derivative and the partial derivative at the utilitarian level is cosmetic. You simply assume all other variables to be constants and you differentiate with respect to the variable of interest. However, the moment the functions become more complicated and they become nested, messy chain rule extensions kick in. I think it's best to remember the biggest one, or at least to remember its structure. It is unfortunately unavoidable that you will eventually memorize this because there's so much differentiation in your various modules, not just this one. And so your entire workshop today is just differentiation, differentiation, differentiation. You will be differentiating till you drop today, and there's a good reason for that because it's an absolutely essential skill. Any questions?